Hi, hello. Welcome to this webinar. Today, this webinar will be presented by Roman Martin and myself, Ronald Siat. This webinar is about geomaterial model applications in CivilFEM 2016, and take into account that this will be one of the applications of CivilFEM material models. Today, we will talk about slope instability under seismic loads, one of the nonlinear applications of and powerful tools of CivilFEM. About or applied to geotechnics.
Well, one of the applications of these nonlinear material models is for slope instability is the shear strength reduction method. This method is based in the soil. For the soil materials, the properties are reduced by a factor until the loss of stability. The material strength depends on the material model. Different parameters are reduced by this factor until the failure happens. This failure corresponds to the non-converging. This failure corresponds to the non-converging material model. In the case of Mohr Coulomb, we have two parameters to determine the yielding surface. That is the cohesion and the friction angle. In this case, both parameters are divided by this factor. So the yielding surface is reduced in this way from black to red line until the material properties are reduced and the stability is lost and failure happens. The model doesn't convert. So this reduction factor will correspond to the safety factor of the slope instability. For other material models like Hook and Brown or any other, this method can be applied, and just the yielding surface is reduced by a factor. For this material model, when we are solving and the material properties are reduced, we will obtain the sliding surface that will correspond to the soil yielding. The soil yielding will delimitate the sliding surfaces. This method will give us is more useful because it will give us more realistic stress strain behavior, and also will provide information on the deformations. When the safety factor that we are using to divide the material properties will be around 1, the stress strain behavior and the deformations will be the realistic ones that we will have. If that safety factor is bigger, 2, 3, an example, of course we are reducing material properties, so deformations will be bigger and strains will be different. But if we have some conditions that will reduce our material properties, such as water table increase or any other reason, the sliding surface will happen following these yielding zones. So here we have two examples about the yielding zones. And this method eliminates the needs for a priori assumptions or failure mechanisms. We don't need to predefine any yielding surfaces, any sliding surfaces, where to analyze the equilibrium, such as the limit equilibrium methods. And that is to calculate the safety factors. For applying seismic loads, there are many methods that can be used. The most basic and extended is to apply a pseudostatic analysis and apply an equivalent horizontal acceleration. This method can give us the horizontal acceleration where yielding will happen, and also using this method and applying the the seismic acceleration as a permanent body force, we can estimate the safety factor of the slope using the previous method. But well, the limitations of this method is that the force is considered like a permanent horizontal load. This is not realistic, and these accelerations only due to the seismic behavior will be only applied during a short times. So the next method, new Marc displacement method, what it does is considering the accelerations that are over the yielding acceleration, the acceleration that generates yielding and displacement on the slope, considering those peaks, those acceleration peaks, where displacement happens, integrating those accelerations will give us the velocity of the mass, and integrating it again, we will get the displacements that are calculated as a rigid plastic body that is sliding on on the inclined plane on the yielding surface. Well, this is an approach. We can use CivilFEM with static analysis to calculate the safety factor of the given horizontal acceleration. We can calculate also the yielding accelerations that will generate displacements, and also integrating the accelerogram will give us an idea of the displacements. But the best of using finite element models like with a software like CivilFEM is being able to solve a full transient nonlinear analysis, applying accelerograms and calculating the realistic displacements and yielding surfaces and zones in the model. So we will review them all in a couple of examples. First, we will study the Alhambra of Granada, and then we will study a 3D model. This will be done in a 2D model, and then we will see a 3D model where we analyze the effect of a building on top and how to reduce displacements in that building.
Well, we consider always that these methods that will be presented today are more accurate than the classical methods that already everybody know. All the classical methods that there were the slices are taken into account, and forces and equilibrium are taken on each slice, and you have to create the circles and tangents, and after that you obtain a safety factor as well. But we consider that these methods are more accurate and more visual and more easy to
and also the most important is that they have no limitations in the other classical methods like limited equilibrium methods. You need to consider vertical soil columns to calculate the equilibrium. Here you can add anything to the model, any sort of loads, any sort of way to model faults in the terrain with contact elements. Anything can be added to the model, and then you solve it, and you are reducing the material properties and obtaining the safety factors. So this is much more wide, has more widely applications. Well, starting with the Alhambra of Granada, this is a palace that is on top of a hill, and on the bottom there's a river. Due to the effect of the river, the slope was increased, and we are going to analyze the safety factor of this slope, and also how to improve that safety factor with some anchors. And we will follow the three possibilities, applying applying horizontal load, solving a static analysis, and applying horizontal acceleration on the model, and also from that option solving a static analysis to a full nonlinear transit analysis. So if we open here
We have many models created with different configuration of anchors, and we will present you today. You already know this graphical user interface. It's being always updated and improved.
Well, this is the model, the slope 2D model, and we have here different strata of the model. So here, the loads we are applying is the gravity with a vertical acceleration, and for the seismic loads, we are considering, in this case, only a horizontal acceleration of 0.28 Gs. We could also consider a vertical acceleration that will increase the gravity load and will generate sliding. We will also consider the Alhambra weight. The Alhambra weight is on top. Here we can see. And just one important tool of CivilFEM is that any load like this could be converted into mass. Just clicking here, we can convert it into mass, and the accelerations will affect them. The accelerations can affect in all directions, or we can modify just to select any direction we would like. So we can decide how to apply it. And then, well, we define our load case. That is all the three loads together at the same time: gravity, horizontal acceleration, and the weight of the Alhambra, of the tower. Then we are applying this method that we are reducing the material model values, cohesion and friction angle. We will reduce by a coefficient. What we have done is starting with 0.75 as the safety factor. It means that it increases the strength of the model, and then that factor is being increased until the model stops converging. So results are saved, and every result of this safety factor corresponds to a different result file. If we open those result files, we can see that in the first one, that corresponds to 0.75, the safety factor. You can see an example, horizontal displacement in the model. Well, we can see there is about 10 centimeters horizontal displacement due to this seismic acceleration. Also, one tool of CivilFEM is seeing the total displacement that can be plotted with arrows. That is easier to see. Well, we can see the same zone. We are having mainly horizontal displacements. Well, the model, the model, if we advance till the end, the last step that convert, we can see that displacement on this part is around 13.5 centimeters, and then instability happens. This instability is happening with a factor equal to 1. It means that the safety factor of the slope for this seismic horizontal acceleration is equal to 1. So we can say that this slope there's no security, and it should be reinforced. If we plot equivalent plastic strain, we can see here that the jailing is happening. In the base of the sliding surface, the plastic strains will be very big. So we need to modify the range to be able to plot the whole yielding zones. We're using example 0.005. And well, we can see that the yielding surface is around this part. And we can see, if we go backwards to previous safety factors, in 0.99, the safety factor, some yielding zones in the base, but just small, and if we reduce, no yielding, and suddenly yielding happens when we arrive to 1, to the safety factor. So we can see the instability happens suddenly. If we plot history plots to plot all results together, we can with this history plot, we can plot, in example, displacements of any of these nodes versus a safety factor. So we can determine also if there's a point with with a safety factor that corresponds to a high displacement increasement. It can happen that even if the model converts for a higher safety factor, we could determine that the deformations are too big. So we could decide to reduce the safety factor to some allowable deformations, like in example 10 centimeters, whatever. Here, if we select a node here, an example 386, and we plot that value, we can see, as we saw before, that displacements are around 8 centimeters, and suddenly for this value, just instability happens and the model stops converging at this point. So we can determine that the safety factor is around 1. So taking into account also this yielding zone, we have designed some anchors, some pre-stressing anchors in this zone just to try to improve the behavior of this slope. So if we open model,
when we have nonlinear models, we can always divide our converged solution into different log cases. Here in CivilFEM, we have different files, each file for each log case converged. Here you can see that we use one of the utilities of CivilFEM, which are the insertion. We have used insertions to define anchors along the slope. This configuration of anchors are defined using what we call here in CivilFEM structural elements, and we don't need to define a very exhaustive mesh or coincident mesh, because the insertions will couple will tie the degrees of freedom of each structural element. So these anchors are already inserted into the host structural element. In this case, will be the different strata.
The anchors are divided by 2 different structural elements. One of them is a cable. This cable is not inserted, so it is only merged in the node outside, and the rest of the cable is free. The only part that is inserted in the soil is this other part, the bulb of the. And also we have applied a pre-stress load on these tendons that is equivalent to about half of the yielding stress of the tendon.
Yes, here you can see if we zoom the elements, how we define here you have the geometry, and once we mesh, we will obtain our different structural elements, and here we can decide in the utilities which elements to be inserted.
We have solved it also the same loads: the horizontal acceleration, the load of the tower here, and also the pre-stressing loads on the cables. And have also started in 0.75 the safety factor, and solve it by 0.01 the increase of the safety factor, until the model stopped. And we saw that the model stopped exactly in about the same safety factor as the previous one. So if we study the yielding zones, and we will try to see why we didn't improve the behavior of this slope. So we can plot first the displacement, horizontal displacement. Well, we can see we are still having here some big displacement that they were a little bit reduced in this part, but they are bigger like in this other. If we plot equivalent yielding stress, equivalent plastic strain, here we can see that, well, just reducing a little bit the range for seeing it easier, we can see that previously the yielding zone was coming like here around, so we have, due to these anchors, we have modified it in these zones, but it is still crossing around these anchors, and we didn't solve the sliding of this zone. We modify a little bit, but we couldn't improve much the behavior of this. If we plot the results, this is the old results. We are opening the new ones.
Here we can plot any results versus, in this case, well, we call it time, but it's the different.
Yes, if we plot the safety factor against displacement, we can see that the displacement doesn't happen suddenly. It's like more ductile behavior, but also around 1 is the safety factor. So this model this configuration of the anchors is not good enough. So we go to the next configuration, that is increasing the length of these anchors and adding some more anchors in these zones. Well, this is the new configuration here, where we have added some more anchors. And we have also solved, starting with 0.75 and just waiting for the model for not to convert. And we found that the CivilFEM solved it till 2.72. That is the safety factor. So we have increased the safety factor from around 1 to 2.72. So we can see that this reinforcement is working. If we open the last load step that could convert, and we plot also X displacements example, we can see, well, we are having here big displacement 2.65. That of course they are too big, they are not allowable, but well, that is the last safety factor where the model converts. If we plot the equivalent yielding, the equivalent plastic strain, we can see now the sliding surface follows this shape. So we have modified, well, we have also some yielding zones here, so it's like divided into 2. If we just reduce a little bit the range,
now we can see that this slope is we can consider more safe.
We can see safer. That like 3 different yielding surfaces are happening. This big one through here, other small one that comes here to the river, and also a second cut here. But the one that is yielding is this one. But what we saw, we are having, for this safety factor of 2.7, we are having big displacements. So we can plot displacements, one of these nodes versus safety factor, in order to determine a more reasonable, lower safety factor for taking into account displacement. So this node, in example 4441, we will use that node. And we are adding the new results that are here. To here. And we are plotting the displacements. Well, we can see here displacements, just the loss of stability. start happening is around 2.5 or displacement bigger than 1, and we could determine an allowable displacement lower than 10-15 centimeters around here, so we can at least say that the safety factor is around 1.8, 1.9. Well, this is to determine the safety factor for the horizontal load, the horizontal acceleration that we have in our model. The next step is just trying to determine, like the new Marc method, the acceleration, the horizontal acceleration that generates yielding and starts the displacements, the sliding between the block of mass and the other part. To calculate that could be used for the new Marc method. Well, these are the here we can open model, and for the new model we have two configurations as well. And well, in this model, what we have done is, instead of reducing the material strength, reducing cohesion and friction angle, what we have done is increasing horizontal acceleration, keeping those values equal to 1, and we have increased the horizontal acceleration until the model stops converging. That is, the sliding happens and instability occurs. So, we have started with only the loads of the weight of the tower, self-weight, and zero horizontal acceleration. And we have increased the horizontal accelerations until the model stopped converging. If we analyze the results, we can see that the model started, this is 0.1 Gs. We have solved it for every 0.01 G increment, and we can see that the model stopped converging for 0.55 Gs. We can see that for that value, well, it's about 2 meters displacement, which is very big. And if we plot equivalent plastic strain, we can see that for reducing, as there are big yielding zones on the bottom, we have to reduce the range to be able to see it better. And for more logical range, we can see that for data accelerations, different yielding zones are being generated. If we plot, as we did before, horizontal displacements versus acceleration, in this case, we select the new results, and if we plot horizontal displacements versus just horizontal displacement versus the acceleration, this is the G coefficient, we can see that we have like a drastic deformation, a linear deformation until around 0.38 or whatever. In that point, instability happens and big displacements starts happening. So we could determine that for acceleration higher than 0.38, around it, we have the yielding the yielding acceleration. So well, with CivilFEM, like a summary, we can determine that for a seismic load of 0.28, the safety factor is around 1. The first configuration of our anchors didn't improve much the behavior of this slope, so we decided to solve a second configuration. The second configuration gave us a higher safety factor and also different yielding surfaces. Well, then for the previous slope, also we try to obtain the maximum average horizontal acceleration of failure mass. That happens around 0.38. That value could be used for the new Marc method to determine, with this static horizontal analysis, to determine total displacement by integrating the accelerogram for accelerations higher than this value. But well, the best method to solve that, to calculate displacement, real displacements, is to calculate the full transient analysis. In these situations, we can apply accelerograms or also displacements on the base with tables. For these models, we need to apply damping boundary conditions to avoid the waves to rebound on the boundaries. So we need to define here boundary conditions. We have in CivilFEM, we have damping elements that could be applied to the boundaries, and with those boundaries, we'll avoid the rebound of the wave. We can see here, if we repeat the video, that applying the accelerogram, the yielding zones start happening. This is the first anchor configurations where the yielding happened, the surfaces happened and didn't improve much the slope. When we applied this accelerogram to the slope without the anchors, the model didn't converge because the slope, the instability happened, and with all the anchors we didn't obtain practically no yielding. So this one with this second configuration has equilibrium, but a lot of yielding zones and sliding surfaces. And well, the next model to analyze is a 3D slope, where we calculate the safety factor in similar method, similar as we did before with the CR strength reduction method, and we calculate a safety factor, but also we measure the displacement here close to the building. As they are not allowable, those displacements, we design an anti-slide pile, some anti-slide piles, here a line of anti-slide piles to reduce the displacement of this building.
This case is 3D model, where you know that it takes more number of elements and nodes. The only thing is that will take you consume more time and resources. But well, as Roman explained you, here the methodology is the same. We just follow the same procedure of the safety factor and reducing the some of the properties.
Well, here in this case, we not only considered the gravity, also we did apply some other loads, such as the overloads of the building, we can see here, and also wind loads on the building. Wind loads that can increase the effect on this part of these footings, and to reduce the safety factor of this slope. Also, well, we considered the gravity, and in this case we didn't consider any horizontal acceleration for the seismic loads. We could also consider them. We started, in this case, with a safety factor of 1.05, and we increased the safety factor by 0.05. Just as we have a bigger model and every result file is big, so we decide to reduce the number of files to be created. If we open the result files, we can see that we started with 1.05, the safety factor, and the model stopped in 2.0. If we plot the results in that, we can see horizontal displacement. Well, we can see that the slope is having horizontal displacement, more or less the same in it all. We can also plot the total displacement with arrows. And well, we can see that we are having big displacement on the building as well, following the slope, and we could try to reduce it. And well, now let's see the yielding zones, because we will try to apply these piles on the yielding surface to reduce it. So if we plot the equivalent plastic strain, we can see that there are big yielding zones in the base of the slope, also by the foundations. We are going to reduce it for being able to see more yielding zones. Well, we can see it's like a sliding surface here, and the way to see inside the solid elements is using the view utils here, and we will apply a cut on the model that will move around y-axis, y positive axis, and I will click 3D. So with this option, we can use this scroll to see inside the model. So well, we can see that there are some yielding zones from the building footings that connect to the sliding surfaces of the slope. We can also reduce it a little bit more, the range for an example 3.
This clipping utility will be available for next release. It's very useful to see inside solid elements.
Well, we can see here that the yielding surface is almost just to finish on top in the other zones, but under the building the yielding zones are closed and the instability happens. And also, if we plot displacements on one of these nodes, here on one of these nodes we can plot displacements versus safety factor. We open the results.
These history results are the utilities. It's available in current service pack 4. And as well, you can use it for these nonlinear cases or for typical transient analysis, where you can usually have more than one result file.
So well, we can see that even if instability happens for a high safety factor around 2, we have here in that point 0.35 centimeters horizontal displacement. So well, I would like to reduce those displacement to 10 centimeters. For 10 centimeters, my safety factor is just 1.4. What I will do is to apply to add here some piles to try to reduce the displacements. So if I can reduce the displacements, I can improve the safety factor, just trying to have less displacements on the around the building. So well, that is the second model. We have here Well, here we can see we have the piles inside the soil. These are just a line of piles, and we just model it. We just did it here in a small part. And well, just by solving with this model, we can calculate not only the safety factor of the slopes, but also we can obtain forces and moments on the building, on these piles, and also to design them by code to calculate reinforcement amounts. So well, we solve it in the same way from the same safety factors, starting with 1.05 and until a safety factor of 2. If we see for the safety factor of 2, we see now the yielding zones. Well, we can see we have also the biggest yielding zones here on bottom, and also, well, just the piles are reducing the yielding here around. We have to reduce it a little bit to be able to see more yielding zones. Well, we can see that sliding surface is here around, and if we use the same tool as we did with the previous model, we can see now that these piles are cutting my yielding zones and are reducing the displacements. But well, yielding is happening after the piles. When the piles are finished, we have the yielding, the sliding surface. And well, here the others, due to the building, that due to the piles, they don't connect to the other part. And well, suppose it's working, we should also plot now displacements versus safety factor to see, well, if we could improve the behavior and reduce displacements, or if we have to modify the piles configuration. In this case, well, we can see we reduce a little bit the displacements. Now for 10 centimeters, the safety factor is around 1.45. So we have improved a little bit the displacements, but well, didn't improve much, and we are having, after that safety factor, bigger displacements that are not allowable for this model. So we could decide any other configuration and any other possibilities like reinforced air, doing inserts of different bars here, anchors, modifying, just adding here a weight, modifying the slope, just and see the best solution of them.
In CivilFEM, you can always perform the geometry and create the geometry very easily. You can use our own graphical user interface, or always get it from external CAD.
Well, just like a summary of this, of one of the first geotechnical material models that we are seeing in these webinars, is the strength reduction method for slope instability that can give us much more information of the model using the CivilFEM nonlinearities. Also, we can mix these nonlinearities with code designed by code and any other configuration. Like, well, here we can see that also we are obtaining one of the advantages of this method is that we are the method provide information about deformations and stress strain behavior. For safety factor around ones are the real ones that we will have. For biggest safety factors, they correspond to a weaker material. That could be a possibility that if the material strength is reduced by any other possibility, it will be the failure method we will obtain. So we don't need to define any failure mechanisms. This method automatically gives us the failure mechanisms, and also it allows us to generate much more complex models to take into account like this model, the whole gallery here. Also, we can redesign this gallery to calculate reinforcement amounts to get different failures. Also, it could be, this method could be applied to the different geotechnical structures like foundations, retaining walls, or dams, to obtain the critical failure mechanisms and also to obtain safety factors that could be similar to some safety factors that are defined by the geotechnical codes and standards like the Eurocode 7. So where we can obtain the capacity of the resistance of a terrain using this method and being sure of the safety of our models. And it also allows an integrated structural geotechnical design, because we could, after generating the model, being sure of the safety factor, we can use the results to design by code to calculate reinforcement amounts. So we can see that CivilFEM, CivilFEM nonlinearities, using CivilFEM, the barriers of the nonlinearities are reduced because they are easy to use, and with the friendly, easy to use graphic interface, we can avoid all these problems with a creative solution. Well, thank you very much for your attention.
Yes, just take into account that, as Roman explained you, that CivilFEM has many tools to accomplish this kind of not only geotechnical, but this webinar will we have talked about the slope instability, but we have many other material models and many other capabilities that can be shown in the next webinars. Here you can see our webpage, CivilFEM.com, and here you can always very easily register. If you have already registered, you can log in and get a free version of the software. And always see our next webinars here and on all our videos.
Well, as Ronald said, you can download from the website, and also you can connect us to get a educational version. Also, you can contact us or here in the website you can see the nearest partner. Here our partners, you can contact them for further information, for a demo model, benchmark, or to get the software.
And always you can follow us using all our social media, Facebook, Twitter, Google+, YouTube, and LinkedIn.
Yes, and you can connect also to our channel in YouTube, where we have some other webinars and so much more videos you can find. Sure, you can find interesting.
And for Spanish speaking language, we will present as well this webinar in Spanish next month of June. So be okay. Just check our website to see our next set of webinars in Spanish.
Thank you very much.
Thank you very much. Bye bye.